okay? So let's talk about the acceleration vector. So remember, any change in speed or direction indicates acceleration, okay? So that can be speeding up. This is what we were talking about in the clicker question, right? So if we're going from a smaller velocity to a bigger velocity, that's speeding up. It can also mean slowing down, which means going from a big to a small velocity. That gives you an acceleration in the opposite direction of your velocity, all right? Or it can be turning. Look, here we have the same length vectors, but they've changed direction, and therefore we have an acceleration that points this way. And how do we get this acceleration? Well, for these, you just take, it's always this minus this minus this, and in this case it would be this minus this. So you just flip this one around, pull it over here, and you'll notice this would connect the dots for those two vectors for some visual vector subtraction, okay? All right. Oh, I meant to change this, but okay. Oh, go good. It keeps the answer up there. Yeah, so anyway, we're going to do this one. Which one causes the car to accelerate? And ignore the clutch, because I should have picked one that wasn't a stick shift. Okay, please discuss. We'll vote again. Yay! Okay, what does this change? Speed. What does this change?
Direction.
So what is the answer? Both. All right, all of these things accelerate the car, even though one of them is called the accelerator. This is like a fun physics teacher joke. We're like, this is also an accelerator. Anyway, I'm glad you guys enjoyed it as much as I did. So let's talk about acceleration in 2 or more dimensions. Remember, since acceleration is a change in velocity, it changes by changing speed or changing direction, right? Oh, cool. Now we're doing this again. All right, I guess we'll do one of these. Let's take a minute, and can you guys look this problem over, and then we'll set it up and we'll do it together. So we have this particle that's initially traveling at 6 meters per second at an angle of 30 degrees northeast. It then accelerates at a constant rate for 5 seconds to a final speed of 6 meters per second, but in a different direction, so southeast. And we want to know the acceleration, and then we also want to graph acceleration, velocity, and time, and also velocity versus velocity. So in order to do this, this is a 2D problem where we're given initial velocity and final velocity and time, and we want to find acceleration. So we can set this up graphically, and we also can find the acceleration. So starting with the first part of the problem, we want to find what is the acceleration, okay? So just looking, we want to figure out the kinematics equation. Well, we know that this is our best kinematics equation for this. V final is equal to V initial, where these are vectors, plus A delta t, which we can do because we know these are all vectors, and also because we know that, what's it called? We know the initial and final velocity, and we know the acceleration. We know the acceleration is constant, okay? It says specifically that the acceleration is at a constant rate for 5 seconds. And we're given time, right, 5 seconds. We have our initial and final speeds, which are actually velocities because they're given with angles. And then we want the acceleration. The other thing we want to calculate down here are these different graphs, which we'll do secondarily. So we'll start with just a picture of what the vectors look like. So this would be our Vy direction, and this would be our Vx direction. These are both in meters per second.
Can you draw a heart?
Fluffy, I'm doing a problem for my class. Can you wait? Okay, I'll draw a heart. Are you happy now? Okay. How's that?
Perfect.
Okay, can you go take a break? All right. So getting back to our vectors, our initial velocity we can plot, it looks like this. Oops. And our final velocities look sort of like the mirror image of it. Oops. Like this. This is our velocity initial, this is our velocity final. Remember, these are equal to 6 meters per second, so that these things have a length of 6, and they have an angle of 30 degrees, and this is an angle of 30 degrees. Now, this one, remember, this is northeast, so that's north, right? So if we have north, south, west, east, so that's going to be north, this is east, north of east, okay? The other one is south of east. So that's how we determine these angle directions. If we break down our velocity vectors into components, then we end up with these two components and these two components, which should be about equal. So you can see in the y direction, these two should basically cancel. In the x direction, they could add, right? So just to give you an idea of what's going on, we'll get the actual values shortly. But going back to our first problem, we want to figure out
how you get out of the book things.
Okay, so you can break this equation right here into x and y, so that we'll have v final x is equal to v initial x plus a x t, and then v final y is equal to v initial y plus a y t. And so we can pull these apart and we can treat them separately. And that means that our ax is going to be equal to v final x minus v initial x over delta t. Our final velocity, remember, is in the x direction. These are the exact, you can see these vectors are exactly the same. So this is going to give us 0 meters per second squared. And then our ay is going to be v final y minus v initial y divided by delta t. So that's going to, we're going to have to calculate that. So this vy should be 6, and this would be, since this would be this side of the triangle, this would be 6 sine of 30 degrees, which should give us, remember sine of 30 is 1/2, so that's going to give us 3 meters per second. So this one is also 3 meters per second. So this is going to be, the final one is negative 3 meters per second, and that's going to be minus 3 meters per second over 5 seconds. So this is going to give us negative 1.2 meters per second squared. So that's ay. So our ax, if we're keeping track, ax, acceleration in the x direction is 0 meters per second squared. Acceleration in the y direction is negative 1.2 meters per second squared. So our acceleration is only in the y direction. And if you want to write acceleration as a whole vector, it's just going to be negative 1.2 meters per second squared y hat. That is our acceleration. So I'm going to make this a little bit smaller so we have room to make all these graphs. And then we're going to make all the graphs. And the other thing we want to do is, you can see this would be 6 cosine of 30 degrees, which should give us, both of these should give us 5.2 meters per second. Okay, so that's our, so remember our v sub x initial is equal to our v sub x final, which is 5.2 meters per second. Our vy initial is going to be 3 meters per second squared, and our vy final is going to be negative 3 meters per second. Sorry, not squared. Okay, so if we want to draw all these graphs, we can find the different components of velocity. So in the y direction, we're changing. So in the y direction, let's say we do velocity y versus time. We start at 3 and go to negative 3. So let's say we start at 3, we end at negative 3. That's going to be 5 seconds later. So this would be 3, this would be negative 3. This is all in meters per second, and this is time in seconds. Okay? We can duplicate this to do this in the x direction. So we'll erase these. So in the x direction, so we'll change that to x. In the x direction, we see that the velocity is the same the whole time, and it's 5.2. So that's going to be 5.2 meters per second all the way. Remember, this is 5 seconds. This is 5 seconds. Okay, so those are our velocity graphs. I'm going to make them smaller so we have some space. We can also get acceleration versus time. So I'm just going to clear these up. We still want the same time. So if we plot our acceleration in the x direction, acceleration in the y direction, those units are meters per second squared. We can see the acceleration in the y direction is negative 1.2, and it's constant. And the acceleration in the x direction is 0, which is also constant. Okay, so that's all of our graphs and all of our questions answered. Yeah, those are what the graphs look like. Okay, let's talk about acceleration in 2 dimensions. Also, as a side note, when I rented this manual car, the parking garage you have to get out of, the only way to get out was an uphill spiral ramp, which is like, I've driven like 5 different manual cars throughout my life, but a new clutch is always a new clutch, and so going uphill is like the worst way to start. Also, it's like a modern car, so it doesn't have like a parking brake I could use to cheat to see what the RPMs are, and I couldn't hear it because it was so quiet. I was like, is it revving? I can't tell. So, fun fact. Okay, so let's just look at that again. This is a hockey puck that I've drawn for you. So this is what we call an instantaneous force, because remember, acceleration comes from force. So it just gives this thing a little tap. If we plot the positions at the same time intervals, here's our little snapshot graph of what's going on. So here, I'm going to draw in all of the velocity vectors, okay? Maybe, if they're going to show up. Cool. So here's all the velocity vectors. What do you notice about the velocity vectors? They're all pretty much the same size, but they've changed directions, yes. So these are our velocity vectors. Now remember, we're going to call this x, right? This direction is x, and we'll plot all of the components of the velocity vectors in the x direction. So you'll notice the velocity vectors here are the same size as the regular vectors, but over here, there's two components. So here, these would be our velocity vectors in the x direction, and then you can also get your velocity vectors in the y direction. Hopefully you can see those. They're this very faint green, okay? So if you want to, yeah, so when I got fancy with the animation. If you want to plot these on an actual plot of x and y, then you can break in any velocity into x and y. And remember, multi-dimensional motion can be modeled as independent motions, okay? So as soon as that thing got tapped, it didn't change anything about the motion in the x direction, but it did give it a slight amount of velocity in the y direction, which caused it to turn, okay? So remember, we did all of these. These are the ones we derived in the last chapter. These are our kinematics equations. Now they're written in full vector form. How many do we have in 2D?
6.
6, right? So we have the x ones. Oh, wow. Why did I do this? Okay. And we have the y ones. Oh, good. We're not going to swipe all of those. So now we have, for every vector, right, for every motion, you can break it up into x and y. And if we had z, we'd also have z. Okay? Now let's this is a lot to take in, but we'll apply it to something that happens all the time.